Good morning, everyone, and thank you for joining my presentation. I'm Enjun Du from the Hong Kong University of Science and Technology, Guangzhou. Today, I will introduce our EMNLP 2025 oral paper titled The Mixture of Nuns and Pruning Experts for Logic Graph Reasoning, or simply MOKGR. This work was conducted together with Si-Yin Liu and Professor Yongqi Zhang. I will begin with the background and motivation of logical reasoning, then I will explain our proposed MOKGR framework, focusing on the two Q components, the mixture of nuns and experts and the mixture of pruning experts. After that, I will present our experimental results and key findings, and finally, summarize our main contributions. Logic graph reasoning aims to infer missing facts from a structured graph. Each fact is a triplet, such as a head, relation, and tail. Given a query like HR, our task is to predict the correct answer entities. For example, given this logic graph, if the query is Jack watched, we want to find the Avenger and games as the right answer entities. Logic graph reasoning can be divided into two settings, translative, where training and inference graph share the same entities and relations, and the second one, inductive reasoning, where some test entities or relations are unseen during training time. The inductive setting is more challenging, since the model must generalize to unseen entities and relations without memorizing the graph structures. However, existing GNN-based models still suffer from two key limitations. First, they lack query-specific path explorations. They use a fixed number of hopes for every query, even though different queries may require different reasoning depths. As shown in table on the right, we have calculated the hopes at which the correct answer first appears for different queries. The results show that the correct answer appears at different positions for different queries. For example, for WN18RR, about 32.9% of correct answer appears as hope 1, while about 17.9% of the correct answer appears at more than 5 hopes. Second, as shown in the left, their pruning strategies are uniform. All paths treated equally, without distinguishing between informative and irrelevant ones. To perform effective reasoning, we need personalized path exploration, selecting both the optimal path lengths and the most relevant neighbors for each query. To address these issues, we propose MOKGR, a new framework composed of three models: an RD graph based neighbor index, a mixture of nuns experts, and a mixture of pruning experts. Together, they allow the model to adaptively decide how deep to explore and which node to keep during reasoning. We first introduce the mechanism of our RD graph. Unlike previous models that use GNN messaging passing, where all entities pass messages to their neighbors at each layer, our approach starts from the query entities and pass messages to its neighbors, then further propagates messages from those neighbors to their own neighbors, and so on. In this way, our model not only significantly reduces computational cost while preserving the effectiveness of information propagation, but also mitigates noise accumulations. Next, We introduce the core components of our paper mixture of nonce and pruning experts (MOKGR). For the given query, Jack watched, we treat Jack as a query entities. First, we compute the required reasoning nonce, then start message passing from Jack by indexing its neighbors. After indexing, messaging propagation is performed, followed by a pruning step. We can observe that no entities are pruned in the first layer. Then, we continue the neighbor indexing in the first layer. After the second layer, we obtain 6 entities, upon which pruning computation is conducted. We can observe that Taylor Swift is pruned out at this stage. Finally, we continue performing neighbor indexing and pruning. As shown in the figure, the reasoning graph is our final reasoning knowledge graph, where blue nodes represent the return entities and the green nodes denote the correct answer. Our model can be divided into 3 steps. Let's begin with step 1, the mixture of nonce experts. Given a query such as EQ, RQ, our goal is to adaptively determine how deep the reasoning should go. To achieve this, we first compute a contextual embedding CQ that integrates both structural information and semantic information derived from the relational neighborhoods of query entities and semantic information captured from the query relation embeddings. We then use CQ to compute the compatibility of each path length experts through the learnable projections. In simple terms, each expert corresponding to a possible reasoning depth, and we evaluate how well each one matches the current query. After that, we apply a softmax function to calculate the importance of each path length. This process dynamically adjusts the reasoning depth depending on the complexity of queries. Finally, we combine the outputs of different experts to compute the final reasoning scores. As a result, MOKGR can adaptively select shorter or longer reasoning paths, avoiding unnecessary computation while maintaining high reasoning accuracies. Next is step 2. We will introduce the mixture of pruning experts. After determining the reasoning nonce, we further need to decide which entities and paths to keep. During propagations, to achieve fine-grained personalizations, we design 3 complementary pruning experts, which can be divided into scoring experts, attention experts, and semantic experts. The scoring experts evaluates each entity based on its overall contribution to reasoning, using the layer-wise reasoning scores. The attention experts analyze the structural patterns, focusing on entities that are highly connected or play key structural roles. The semantic experts ensure semantic coherence by measuring the cosine similarities between the query and entity embeddings, keeping entities that are contextually aligned with the query. Each expert provided a unique perspective, and MOKGR dynamically select and fills the whole performing experts at each layer. As shown in the figure, the mixture of pruning experts effectively remove redundant entities while preserving those most relevant to the query. The mechanism helps the model maintain both efficiency and interpretability throughout the reasoning process. Finally, in step 3, we introduce the training objectives of MOKGR. Our total loss function consists of 3 components. First of all is the cross-entropy loss. which optimize the reasoning performance by comparing the predicted and tuning answers. The second one is importance loss, which ensures that different experts are effectively utilized, preventing the model from over-relying on a few dominant experts. And the third one is load balance loss, which further regularize the training by distributing computational loads across the experts. This loss turn jointly guides the model to achieve a balanced and cooperative expert systems. And here is our experts. We evaluate MOKHR with 4 key research questions. Question 1 is how effective is it compared with existing methods? And question 2 is how does the expert selection mechanism behave? Question 3 is can MOKHR achieve truly personalized path explorations? And question 4 is how do different components and hyperparameters affect the model's performance? Let's begin with Q1, where we evaluate the overall performance of MOKHR across both transactive and inductive settings. We conduct experiments on 6 widely used benchmark datasets. For field comparisons, we follow the experimental setup of a dark probe and evaluate using 3 standard metrics: hit 1, hit 10, and MRR. The table on the left summarizes the results in the transactive settings. As we can see, MOKHR achieves the best or the second best performance across all datasets, significantly surpassing previous state-of-the-art GM-based methods. The bar chart on the right shows the inductive results. MOKHR continues to outperform all supervised baselines by a large margin, with an average MRR improvement of 6.3%. Next, let's look at Q2, where we analyze how MOKHR selected and utilized different experts. The 2-line chart on the top showing the selection dynamics of lens experts and pruning experts over training epochs. We can see that the model successfully learns to select the most suitable path lengths based on the query context. Short paths are favored in the simple queries, while long ones are used only when necessary. Moreover, the gating function effectively separates over reliance on long paths, improving both efficiency and interpretability. For pruning experts, we observe that complementary behavior, the score-based and attention-based and semantic-based experts are selected at different frequencies, each contributing unique perspectives to the reasoning process. At the bottom, the bar chart compares different expert combinations. The result clarifies that the mixed experts concept outperform single experts, confirming the effectiveness of our mixture design, and the adapting weighting performs better than the fixed weighting. Overall, MOKHR achieves the best performance across all metrics. Now we move to question 3, a case study illustrating how MOKHR achieves personalized path explorations. The 2 heat maps show the distribution of relation types in reasoning paths on the family datasets. Each row corresponds to a query relation, and each column represents a relation type encountered in the reasoning path. In region N, the left, the color distribution is almost uniform, meaning it treats all relations equally without adapting to specific query context. In contrast, MOKHR, as shown in the right, exhibit a much more diverse and query-dependent distribution. For example, when the query is about niece, MOKHR automatically highlights semantic related relations such as aunt and uncle, while filling out irrelevant ones. Finally, question 4 presents our ablation study to analyze the contribution of each component in MOKGR. We perform it in WN1SRR and Yagao 310 and examine the three key factors: balancing turns, the noise turn, and the expert's ablation. Overall, these results verify that each design choice, from adaptive lens control to multiple expert pruning and balancing, plays a vital role in MOKGR's strong performance. The last one is summary part. Our contributions are threefold. First, we propose a personalized path exploration strategy for knowledge graph reasoning that adapts to query-specific requirements and entity characteristics. We introduce a novel mixture of expert framework that facilitates personalization in KG's reasoning. The incorporation of both adaptive lens level reading and personalized pruning strategy effectively address the critical limitation of fixed path exploration strategies. And the experimental results on both translative and inductive datasets highlights our model's achievements of superview reasoning accuracy and computational efficiencies. The extensions are also straightforward. Maybe we can establish theoretical guarantees on optimalities convergence to improve the interpretability of MOKGR, or we can scale our model to domain-specific and temporal or large KGs, as shown in the bottom figure is an illustration of TKG reasoning. Maybe we can extend the MOKGR to adapt the temporal knowledge graphs. The last one may be bridging MOKGR and large language models for unified knowledge graph reasoning, where MOKGR maybe provide structural interpretabilities and large language models maybe offer adaptive and context-aware generations. That is the end of our presentation. Thanks for your listening. For any questions, maybe you can visit my homepage and drop an email to me.